Good day to Dr. Muhammad Daniel Hafiz. Today we're going to present our group project, which is dynamic round-robin heuristic in the cloud computing environment for optimal task scheduling. But before that, I'm going to introduce my team member, which is Shafika, Dwight, Laina, and me myself, Hazani. Scheduling in operating system. Scheduling is the systematic arrangement and execution of a task in a computer system, crucial for efficient resource utilization, particularly the CPU. The importance of scheduling in operating system is optimized performance, throughput, and responsiveness, impacting the user experience and overall system functionality. In the dynamic realm of cloud computing, effective scheduling is essential for fair resource allocation, latency reduction, and maximizing throughput. Now, let's explore how the scheduling principles evolved to meet the unique challenge posed by dynamic environment of cloud computing. Introducing the dynamic round-robin heuristic algorithm, or DRRHA, as a solution to intricate challenges of task scheduling in cloud environment. DRRHA also address challenge by varying priorities, resource demand, and arrival pattern. The key features of DRRHA is dynamic time quantum adjustment based on burst time means. The time quantum, which represents the maximum time a task can use the CPU, is adjusted dynamically based on the mean of burst time. This ensures that tasks receive an appropriate amount of CPU time, contributing to efficient execution. Next is consideration of remaining burst time for task completion. By considering of remaining burst time, DRRHA enables timely completion and removal of tasks when the execution concludes. This feature contributes to minimizing average waiting time, turnaround time, and response time. The last key features is incorporation of shortest job first (SJF) criterion for scheduling precision. SJF prioritizes tasks with the shortest expected processing time, aiming for quicker execution. This criterion enhances scheduling precision by optimizing the order in which tasks are scheduled, leading to improved system responsiveness. Next, advantages of DRRHA. Firstly, substantial reduction in the average response time. This reduction is indicative of the algorithm's ability to swiftly respond to scheduled tasks, contributing to enhanced system efficiency. Next is versatility and stability across different workloads. Regardless of the nature of complexity of the task at hand, DRRHA consistently maintains its efficiency. This is crucial in dynamic computing environments, where workloads may vary, showcasing the algorithm robustness and reliability. Last but not least is outstanding efficiency. The algorithm dynamic adjustment, consideration of remaining burst time, and incorporation of the SJF criterion collectively contribute to its overall efficiency. This efficiency is reflected in reduced waiting time, turnaround time, as well as maximized CPU utilization, making DRRHA a competitive solution in diverse computing environment. I'm going to pass this presentation to Shafika for a detailed description of DRRHA.
Before I start, let me introduce myself. My name is Shafika binti Bedru Azmi with matrix number 216427. Now, let me continue with the presentation. In this approach, we've got 7 main steps. First off, when users give us tasks, we put them into a queue in the order of their arrival, like first come first serve method as shown in the diagram. Then we arrange the tasks based on their burst time. Second step, after each cycle, we calculate the average mean for all the tasks in the queue. For the third step, we use equation 1 to determine time quantum for each task individually. In the first step, we let the task execute based on the time quantum that has been calculated before. Now, there are 2 things that can happen when a task finishes its execution. First, if the time quantum is less or equal to burst time left, complete the execution, then take it out of the queue. But if there's more burst time left than the quantum time, we pause it and move it to the back of the queue. In the fifth step, when a task shows up, we use the shortest job first method to organize the queue. Then we update the average mean and quantum time values for each task in the queue. Note that in the equation 1, Qt is the quantum time of task A in round B, M is the average mean at the ready queue, while BT is the burst time or remaining burst time for task A in round B. Moving on to 6th step, after the task finishes, we update the values for all the tasks left in the queue. Finally, the 7th step is to keep repeating all the steps until all the tasks are done. So, that's basically how we roll with this approach. Next, diagram shown is the algorithm and the flowchart which illustrates the major 7 steps that I have explained earlier. So, Al-Haidari and Baharit in 2021 has made a case study on what happens if they combine the shortest job first algorithm with the DRRHA approach. 6 activities with non-zero arrival times were used as in the table shown. In the first round, they sorted tasks based on burst time when task 1 and task 2 arrive. Next, the quantum time and remaining burst time for each task 1 and task 2 were computed. Hence, the schedule for this task is then displayed in the figure shown. In the second round, more tasks are added to the head of the queue, which are task 3, task 4, task 5, and task 6 once they have arrived. This already includes task 1 from the previous round. As seen in the table here, all tasks are ranked from the highest to lowest based on the burst time. Content time and remaining burst time is then calculated for each task. Gantt chart for this round is shown in the diagram. Lastly, in the third round, they sorted the remaining tasks according to their burst time and again calculate the content time and remaining burst time. All tasks were rearranged and executed as shown in the Gantt chart. And finally, the results. Table shown is the summary of overall results including their waiting time, turnaround time, and response time. Now I would like to pass this presentation to Patricia.
While dynamic round-robin heuristic algorithm (DRRHA) can offer advantages in terms of improved performance and energy efficiency, it may also result in increased computing overhead, system complexity, and compatibility issues, which has become problems and disadvantages of this algorithm. The study introduced a unique strategy for enhancing the round-robin algorithm by using the median burst time of tasks in the ready queue. And this method has proven effective in reducing waiting and turnaround time compared to conventional round robin and IRRVQ algorithm. However, it dynamically adjusts RAM properties like latency and bandwidth based on the workload, which might impact system responsiveness due to increased latency from frequent context shift in dynamic environment like DRRHA. Next, integrating the RRHA into existing computer architecture may pose challenges due to compatibility issues with hardware or software system. Existing hardware may not be designed for dynamic adjustment and sophisticated algorithm in the DRRHA, leading to conflicts or inefficiencies. Ensuring compatibility requires careful examination and may necessitate hardware upgrades. Tuning dynamic scheduling algorithm for DRRHA may require customization for specific workloads, limiting its applicability across diverse computing environments and introducing management complexities. Next, DRRHA is responsible for making dynamic adjustment in the algorithm, making it complex, which causes the system complexity. The system needs sophisticated algorithm to assess workload characteristics, predict future demands, and determine the most efficient RAM configuration. Dynamic scheduling algorithm in the RRHA involve multiple parameters that need fine-tuning, and finding the optimal combination can be complex optimization problem. So the shortest job first SJF algorithm outperformed the RRHA in average waiting time and turnaround time, mainly because SJF executes the whole task in one round while the RRHA execute tasks in several rounds. So in summary, the RRHA's dynamic nature, while beneficial for performance optimization, however, it may introduce computational overhead, system complexity, and several compatibility challenges. So balancing the advantages of dynamic adjustment with the challenges is a key consideration in implementing the RRHA in a computing system.
Good day, Doctor. My name is Dwight Kutal, and I'll be sharing our conclusion and recommendations. As we all know, task scheduling is utilized in the operating system to improve efficiency, reducing delays and wait times, and managing CPU's resources better. So, in conclusion, The proposal indicates that DRHA, or dynamic round robin with hybrid average, is an enhancement of the traditional round robin algorithm. So here are the key differences highlighted in the passage. Number one, we have time quantum calculation. So round robin typically uses a fixed time quantum for each task, while on the other hand, DRHA proposes a novel technique for handling the time quantum problem. So it dynamically tunes the quantum time for each task by calculating the mean for all tasks in the ready queue. So this means calculation is based on the shortest job first manner. Secondly, we have dynamic time quantum tuning. So round robin typically employs a fixed time quantum throughout the scheduling process. While on the other hand, DRRHA involves dynamic tuning of the time quantum, where the process of tuning is repeated for each task separately and for each round. So this dynamic adjustment aims to optimize the scheduling performance. We also have handling remaining burst time. So in round robin, generally does not consider the remaining burst time of a task during scheduling, while on the other hand, applies the essential principle of checking the remaining burst time of a task. So if the remaining burst time is less than or equal to the current task quantum, the task is considered completed and removed from the ready queue. So otherwise, the task is stored at the end of the ready queue for execution in the next round. So in summary, these enhancements aim to optimize waiting time, turnaround time, and response time compared to the traditional round robin algorithm. As a group, we find the proposed algorithm to be promising and innovative approach to task scheduling in operating systems. The inclusion of the remaining burst time consideration is particularly noteworthy feature. Thus, we believe that the proposed algorithm distinctive features make it valuable candidate for further exploration and testing. So, for the findings of this study, researchers are encouraged to explore several avenues. First, improvements to the round robin algorithm could involve the development of a novel approach for time quantum calculation. Second, the integration of advanced techniques such as fuzzy logic and neural networks holds a promise for automatically predicting optimal quantum values for tasks, introducing a layer of automation and adaptability to the scheduling process. Third, integrating the round-robin algorithm with other meta-heuristic algorithms to achieve better performance. And lastly, thoroughly evaluate the performance, effectiveness, and robustness of the proposed algorithm and its comparison with other algorithms across different situations.